In the digital age, we are surrounded by technology. Our smartphones, computers, and even our refrigerators rely on a hidden marvel of engineering, the semiconductor. These tiny chips, often smaller than a fingernail, are the unsung heroes of the modern world. They power the devices we use every day, enabling us to communicate, work, and access information at unprecedented speeds. Semiconductors are essentially tiny switches that control the flow of electricity. They can be turned on and off billions of times per second, allowing them to process and store vast amounts of data. This remarkable capability stems from their unique atomic structure, which can be manipulated to conduct or resist electrical current with incredible precision. The journey of a semiconductor, from raw material to finished product, is a testament to human ingenuity. It involves a complex and fascinating manufacturing process that combines cutting-edge technology with meticulous precision. Understanding this process is key to appreciating the vital role semiconductors play in our lives. This essay will delve into the secret world of semiconductors, exploring their journey from sand to silicon and the intricate steps involved in their creation. We will uncover the magic behind photolithography, etching, and metallization processes that transform raw materials into the powerful chips that drive our technological advancements. The journey of a semiconductor begins with an abundant and seemingly ordinary material sand. More specifically, it starts with silicon dioxide, the primary component of sand. This readily available compound undergoes a series of transformations to become the ultra-pure silicon wafer that forms the foundation of a chip. The first step involves heating the silicon dioxide to extremely high temperatures, removing impurities and leaving behind pure silicon. This purified silicon is then melted and formed into a single large crystal using a process called the Czochralski process. The Czochralski process involves dipping a small seed crystal into the molten silicon and slowly pulling it upwards while rotating it. As the seed crystal is pulled, the molten silicon solidifies around it, forming a cylindrical ingot of single crystal silicon. This ingot, typically several feet long and with a diameter of up to 12 inches, is then sliced into thin wafers. These wafers, polished to a mirror-like finish, serve as the canvases upon which the intricate circuitry of a semiconductor chip will be etched. With the silicon wafer prepared, the next stage involves transferring the intricate circuit designs onto its surface. This is where photolithography, one of the most critical steps in semiconductor manufacturing, comes into play. Photolithography is essentially a photographic process that uses light to etch patterns onto the silicon wafer. It begins with a photoresist, a light-sensitive material being evenly applied to the wafer's surface. A mask containing the desired circuit pattern is then placed over the photoresist-coated wafer. This mask acts like a stencil, allowing ultraviolet light to pass through only specific areas. The UV light exposes the photoresist in the areas not blocked by the mask. This exposure causes a chemical change in the photoresist, making it either soluble or insoluble in a developer solution, depending on the type of photoresist used. Section 4. Building up layers. A microscopic masterpiece. After exposure, the wafer is immersed in a developer solution that dissolves the exposed or unexposed photoresist, depending on the process used. This leaves behind a pattern on the wafer's surface, replicating the design on the mask. The exposed areas of the wafer are then subjected to etching, a process that removes the silicon dioxide layer in the desired pattern. This etching can be done using chemical solutions or plasma etching techniques. Once the etching is complete, the remaining photoresist is removed, leaving behind the etched pattern on the silicon wafer. This process of photolithography, etching, and photoresist removal is repeated multiple times, with each layer building upon the previous one. Other processes, such as ion implantation, are also used to introduce impurities into specific areas of the silicon wafer, creating regions with different electrical properties. These regions form the transistors, the fundamental building blocks of a semiconductor chip. Section 5. Connecting the dots, metallization and beyond. With the transistors and other components in place, the next step is to connect them, creating the intricate circuitry that gives a semiconductor chip its functionality. This is where metallization comes in. Metallization involves depositing a thin layer of metal, typically aluminum or copper, onto the wafer's surface. This metal layer is then patterned using photolithography and etching techniques, creating the interconnects that link the various components of the chip. After metallization, the wafers undergo various testing and inspection processes to ensure their functionality and quality. Defective chips are identified and discarded, while the remaining wafers are cut into individual chips, each containing millions or even billions of transistors. These individual chips are then packaged and tested again, before being shipped to electronics manufacturers worldwide. They are integrated into circuit boards and other components, ultimately finding their way into the devices we use every day. Section 6. The future of semiconductors: smaller, faster, smarter. The semiconductor industry is constantly evolving, driven by the demand for smaller, faster, and more powerful devices. Moore's law, the famous observation that the number of transistors on a chip doubles approximately every 2 years, has held true for several decades, but it is approaching its physical limits. As transistors shrink to the size of just a few nanometers, new challenges arise, requiring innovative solutions to maintain this incredible pace of progress. Researchers and engineers are exploring new materials, manufacturing techniques, and chip architectures to overcome these challenges. One promising avenue is the development of 2-nanometer chips and beyond, pushing the boundaries of miniaturization even further. These advancements will lead to even more powerful and energy-efficient devices, enabling new possibilities in artificial intelligence, machine learning, and other cutting-edge fields. Another exciting frontier is the development of quantum computing, a revolutionary technology that harnesses the principles of quantum mechanics to perform calculations that are impossible for even the most powerful classical computers. While still in its early stages, quantum computing has the potential to transform various industries, from medicine and materials science to finance and cryptography.